Good morning. I am Vincent Vijayan, Assistant Professor, Department of Economics, Srinarayana College, Kollam. This session we are discussing the topic input-output analysis, one of the relevant topic in quantitative economics. I hope that all of you seen this pictogram. See, this pie diagram depicts sectoral contribution to GDP of an economy for a particular period. For example, in India, how we estimate the sectoral contribution to GDP. The economy broadly classified into three sectors, namely agriculture sector, industry sector and the service sector. From the diagram, it's shown that the largest contribution to GDP comes from the service sector and the least contribution comes from the agriculture sector. I'm asking a question, does it mean that agriculture is insignificant, or is agriculture an independent sector? Answer is no, never. Why? Any changes in the agriculture sector will make ripples on the entire economy as a whole. Suppose there is the boost in the production of agriculture due to the good monsoon, or that adverse production in the agriculture sector due to the severe drought and flood, both are affecting the entire economy as a whole. The reason is that these sectors are interconnected. We know that in India, many industries are agro-based. See, for example, textile industry, leather industry, tire and tube, jute industry, sugar industry. All these industries depends agriculture for their inputs, otherwise the production is not possible, which means that if any changes in the agriculture sector will affect other sectors also. This is not a one-way relation. See, the reverse is also applicable. Why lakhs of farmers in India are underpaid? The reason is that one of the reason is that lack of communication and transportation facilities. That is why they paid very low amount for their final products. See, anyway, the interconnection or interdependence between various sectors of an economy is economically relevant and scopeful topic. See, such a theoretical framework governed by under the title input-output analysis. So simply, input-output analysis is the theoretical framework illustrating the interdependence between the various sectors of an economy. The first theoretical framework given by Vasily Leontief, a Russian-American economist. For his remarkable contribution in the field of input-output analysis, he won the Nobel Prize in Economics in the year 1973. See, what's the relevance of input-output analysis from the perspective of an economist? Its method is commonly used for estimating the impacts of positive or negative economic shocks and analyzing the ripple effects throughout an economy. See, the impact of there are three types of impacts can be observed through the input-output analysis. First one, direct impact, second one, indirect impact, and third one, induced impact. For example, with an example, I will illustrate how three impacts working. Government launching a new construction of a new bridge as a part of public expenditure program. We know that it constitutes the service sector. It's generating demand for construction materials including cement and other manufacturing materials. It's generating demand for manufacturing products including cement, iron and other construction materials, which means that it's creating direct demand from the output producing by the industrial sector. For the service sector, the manufacturing or the construction materials considered as input, but it's demanding from the industrial sector, and industrial sector itself considered as its final output. See, what is the indirect impacts? See, whenever there is demand for the industrial products by the service sector, it generating income and employment opportunities to the people working in the industrial sector. What is the intuitive or the tertiary impacts of this analysis? See, we know that near the construction work, the worker settlement is establishing some hotels, restaurant is establishing, stationery shops starts to function. Wherever, in all these sectors, some forms of demand is generating. Even it's generating demand for the primary or the agriculture products, which is the part of the agriculture or the primary sector, which means that see, one dose of investment in the service sector generating demand into the industrial sector as well as the industrial sector. Why this happen? All these sectors are interconnected. See, as an economist, what is the scope and implication of this topic? For example, again I am repeating that the government start the construction of a new bridge as the public expenditure program. Then they appointed you, an economist is appointed and they give assignment work is that to study the that the benefits accruing, the benefit generating by this new project. See, in that perspective, as an economist can do a lot of things about this about the input output analysis. See how we can estimate the input output analysis mathematically. See how we can estimate the input output mathematically or numerically. These are the following steps. First one, construct the Leontief matrix. It's denoted by I minus A. Check the Simon-Hawkins condition and identify whether the system is viable or not. If the system is viable, which means that if the system is satisfying Simon-Hawkins condition, the system has a solution, and the solution is that x is equal to 1 by determinant I minus A into, or determinant of IA into adjoint of I minus A into final demand. See, to prove the Simon-Hawkins condition, this is a requirement. Determinant of I minus A should be greater than 0 and the leading diagonal of the matrix should be positive, then the system is viable. And for the solution, we should find out the following things or the following technical aspects. First one, adjoint of I minus A. How we get the adjoint of I minus A? It's by identifying the cofactors of I minus A and make the transpose of I minus A. See, if adjoint of I minus A can get from the transpose of IA, and the transpose of IA can be get by arranging cofactors of the matrix. How we get the cofactors of the matrix? This is the equation, minus 1 whole rise to I plus j, I showing the number of row and the j showing the number of column into minor, and how we find the minor. We can go to a problem, and I think it's very easy to understand how we can calculate input output analysis. This is a problem. An economy produces only coal and steel. These two commodities serve as intermediate inputs in each other's production. 4 tons of steel and 4.7 tons of coal are needed to produce a ton of steel. Similarly, 0.1 ton of steel and 0.6 ton of coal are required to produce a ton of coal. If economy needs 100 tons of coal and 50 tons of steel, calculate the gross output of the commodities. This is a question. From the question, we can make the primary analysis. There are two industries. One is coal industry, another one is steel industry. Steel industry using steel as its input, and also another input is coal. It's producing by second industry, that is the coal industry. For the coal industry, coal itself as a input requirement, along with they are demanding steel, which is producing by the second industry, that is steel industry. And finally, in this problem already given, economy needs 100 tons of coal and 50 tons of steel. See, this is the implication is that, for example, steel producing by steel industry, and it's demanding by steel industry itself. It is also demanding by coal industry, And it's also demanding by the consumer, which constitute consumer directly, investors, the government also. See, in input-output analysis, so suppose assuming that a two-sector model, you first consider the coal industry and steel industry, or the industry 1 and industry 2, but for the final demand you should consider the demand by the consumers, government and investors, and this is denoted by final demand. This is a summation of the question. For the solution, two industries, steel and coal. Steel, it's required 0.4 ton of steel and 0.1 ton of coal. For the production of coal, it's required 0.7 ton of steel and 0.6 ton of coal. And the final demand is given 50 tons for the steel and 100 tons for the coal. From this illustration, we can prepare the input-output table. This is the input-output table, primary step. Two industries, steel and the coal, and the last one is the final demand. And columns showing the inputs requirement, that is the steel and the coal. See how we can read this table. For producing steel, 0.4 tons of steel required, 0.7 ton of coal required. For producing 1 ton of coal, 0.1 ton of steel is required and 0.6 ton of coal required, and this is the final demand. See, for inter-industry relation, first we should consider this technical coefficient, that is 0.4, 0.1, 0.7 and 0.6. See, input-output analysis, first you identify the matrix A. See, first you identify the Leontief matrix. The primary step is that identify the matrix from the input-output table. I already told you this is technical coefficient. This is converted as the matrix A. That is 0.4, 0.1, 0.7 and 0.6. The next step is that correspondingly you should construct the identity matrix. We know that the identity matrix, all the leading diagonal are 1 and above and below are the values are 0. See, this is a 2-order matrix, 2 row, 2 column. So, we correspondingly construct an identity matrix which have also 2 rows and 2 columns. See, the 2 row 1 0 0 1. The leading diagonal are 1. This is identity matrix. And see how we can construct a Leontief matrix. This is Leontief matrix. I minus A. See, take I, the identity matrix 1 0 0 1, and A means 0.4, 0.1, 0.7, 0.6. Once we subtract A value from the identity matrix, we get 0.6 minus 0.1 minus 0.7, 0.4. See, 1 minus 0.4, I minus A. 1 minus 0.4, answer is 0.6. Likewise, 0 minus 0.1 minus 0.1, 0 minus 0.7 minus 0.7, and the last one 1 minus 0.6 minus 0.4. The next step is to find the determinant of Leontief matrix. See how we can find the determinant of Leontief matrix. See, 0.6 into 0.4 minus 0.1 into 0.7. The answer is 0.7. Hawkins-Simon condition is satisfied. Let's go back to the steps of input-output analysis construction. The first step is to construct the Leontief matrix I minus A. Check the Simon-Hawkins condition and identify whether the system is viable or not. Here we construct the Leontief matrix and find the determinant. Hawkins-Simon condition is satisfied, which means that it's a positive value greater than 0. The leading diagonal are positive, that is 0.6 and 0.4 are positive, and the values greater than 0. The Simon-Hawkins condition is satisfied. We can go to the second part. That means the solution part. For the solution part, the first step is to find the minor. This is the Leontief matrix. Already we find 0.6 minus 0.1, 0.7 and 0.4. How we can find the minor of this matrix? See, the minor of first element, that is 0.6, that is the element belongs to the first row, first column. See, this is the 0.6, the minor of this, how we can find the minor of this element. See, leave the first row, leave the first column. Again I repeat that, how we can find the minor of 0.6, leave the first row, leave the first column, the value is 0.4, this is minor of 0.6. Next, first row, second column, that is minus 0.1, how we can find minor, leave the first row, leave the second column, and the remaining value is 0.7, that is minor. And minor of minus 0.7, leave the second row, leave the first column, the remaining value is minus 0.1, that is minor. And this is like the 0.4, the minor is 0.6. How we can convert it, how we can find cofactor from the minor, this is the equation, minus 1 raised to 1 plus 1. This is the order of row and column. We know that 0.6 belongs to first row, first column, that is 1 plus 1. See the case of 0.4, it belongs to second row, second column. See, minus 1, 2 plus 2. See how we can compute cofactor, minus 1 raised to 1 plus 1 into minor. See, I can repeat that, how we can find cofactor. This is equation minus 1 raised to 1 row order and the column order into minor. See, minus 1 raised to 1 plus 1 into minor 4. Answer is 0.4. See, for the minor 0.7, the cofactor is 0.7. For the minor minus 0.1, the cofactor is 0.1. For the minor 0.6, the cofactor is 0.6. This is the equation, minus 1, 2 plus 2. So the value is plus 1 into 0.6 is 0.6. See, in this table, what we done, first we compute the minor, then we converted as cofactor. Next step, transpose and adjoint. How we can find the adjoint? See, from the cofactor, we go these values 0.4, 0.7, 0.1 and 0.6 and converted these values converted these values, that means convert the row as column or the column as row. See here, 0.4, 0.7, 0.1, 0.6 depicted as 0.4, 0.7, 0.1, 0.6. How we can find adjoint? Find the transpose of this given matrix. How we can find the transpose of this given matrix? Convert the row as column and or row or column as row. Here the first row 0.4, 0.7 converted as column, first column 0.4, 0.7. The second row 0.1, 0.6 converted as second column 0.1, 0.6. So we go the adjoint value. This is the adjoint of our matrix. We can move to the final stage, that is the solution. For the solution, X, that is it's denoting the gross output. If we have two industries, there are two output, one is the X1 and another one is the X2. Here it's commonly denoted as X. This is the equation 1 by determinant of Leontief matrix into adjoint of Leontief matrix into final demand. We already find the value of determinant of Leontief matrix. This is a value 0.17. This is the determinant of Leontief matrix. Come to the solution part, 1 by determinant, that is 0.7. Just we find adjoint of Leontief matrix, that is 0.4, 0.1, 0.7 and 0.6. And one more item added, that is the final demand, which means that this output is not only demanded by industry 1, that is steel industry, and industry 2, coal industry, and also it's demanded by or demand generating from the consumers, investors and the government. This is denoted by the final demand. In the question already given, the final demand for the steel is given as 50 ton and final demand for the coal is given as 100 ton. Put these values into the final solution. 0.4 into 50 plus 0.1 into 100, that is a value of 30. 0.7 into 50 plus 0.6 into 100, that is a value of 95. See, 1 by 0.7 and adjoint into demand, that is a value of 30 and 97. Then 30 by 0.7, answer is 176.47. 95 by 0.7, the answer is 558.82. This is a final output. This is a final output of steel. This is a final output of coal. See, in this way, numerically, we can analyze, we can estimate the input output. And before winding up my session, I'm saying what is the economic relevance. If you are appointed an economist by an agency or government, and you know that you have an assignment is that to illustrate the input output or to work out the input output table and illustrate the benefits accruing by various sectors of the economy, you can apply this formula and find the solution. As a part of this class, I am giving two assignment work. Assignment work 1, explain the economic implications of input output model, and assignment 2, see, this is an input output table. See, industry 1 and 2, the inputs requirements are 500, 1750, 1600 and 1600, and the total output given 2500 and 8000. Construct the technology coefficient matrix showing direct requirements. Does solution exist this system? Thank you.